Hello and welcome back to Fluid 2000, lesson number 13. This is the lab prep presentation for lab number 5, which is on regenerative circuits. Regenerative circuits used quite a lot in industry, and they have a special, unique properties. So what is a regenerative hydraulic circuit? A regenerative hydraulic circuit is a circuit used in linear actuators or cylinders that uses fluid from the rod end of the cylinder to supplement the flow of fluid going into the cap end of the cylinder. What this does is it allows you to use the fluid coming out of the system back into the system, and that fluid is injected after the pump, but before the directional control valve. And in this case, you'll notice that we only use one port, and that's port A. Port B is plugged off and not used. Now, in the actual lab demonstration, you will notice that I'm using port B instead of port A. It really doesn't matter. The reason I'm using port B in the lab video demo is it was just easier to hook up the hoses that way and made for a less convoluted looking lab. I must apologize. Some of these labs look like just a lot of hoses because of the tables being fairly small and hard to get everything spaced out so you'd see it like you would on a normal functioning machine. But that's some of the limitations of the lab equipment that we have. So here you have some of the advantages of a regenerative circuit. You can use a smaller pump to run the load. The reason for that is because you're reusing some of the fluid that's coming out of the cap end, and it's not going back into the tank, it's going back into the circuit on the upstream side of the directional control valve, but downstream of the pump, which means that it is already going to be experiencing pump pressure on there. The only reason the cylinder moves is because of the difference in the rod area the difference in the area of the cylinder between the cap end, which is larger than the rod end. The result of that ratio of areas, again, like in other experiments we've seen, has a lot to do with speed and power. Since we're using a smaller pump, we would need less input power. And that's important too, because I can use a smaller drive motor, which uses less power and saves money. I can also use a smaller reservoir, since we are recycling the fluid. I can accelerate the extension speed of the cylinder until I meet the work, and it can reduce a cycle time for hydraulic systems. For instance, if I'm punching out a lot of parts, let's say on an assembly line, and I'm making a lot of brackets, and I have to bend them, and I'm using hydraulic power to bend the metal, I can have basically a two-speed process. The cylinder can extend at a high speed till it meets the work, then switches back into normal using both the A and the B ports to increase the force and bend the metal, but at a slower speed. You don't get something for nothing. So the regenerative action usually only works on the extension of the cylinder. However, if I have a 2-to-1 cylinder, which means that the cap area is twice the area of the rod area, I can use a regenerative circuit both ways. But that's, I wouldn't say rare, but that would have to be designed into the system beforehand. It's not an accidental consequence of using the system. Since the amount of oil required to fill the cap end of the cylinder is partially made up from the rod end of that same cylinder, less oil has to travel through the pump. Less oil is pumped, less oil is needed. We're recycling is what we're doing. The required volume from the pump is equal to the volume of the oil inside the cylinder when it's extended minus the volume of the oil inside the cylinder when it's retracted. So it becomes, again, an area ratio issue. It's equal to the volume occupied by the cylinder rod. That's the difference. The speed is increased by a factor equal to the ratio, again, of full piston area to the rod area, A1 over A2, for example. If the area ratio is 2-to-1, the piston area is twice that of the rod area, this means the extension speed in regeneration will be twice as fast as the extension speed in normal mode. Okay, and there's a couple of formulas down on the bottom of the page you'll notice here. Extension speed in centimeters per second is equal to the flow rate in liters per minute times 1,000 divided by the rod area, and that is in centimeters squared times 60, because there's 60 seconds in a minute. Be careful that you don't get area and volume mixed up. The volume, of course, has to take the stroke into account, and therefore will not be in square centimeters, but will be in cubic centimeters. So just be careful when you're doing that you don't get those two mixed up. Extension time in seconds is equal to the rod area in centimeters squared times 60, which stands for the seconds, times the stroke length in centimeters, how far it has to travel. All of that divided by the flow rate in liters per minute times 1,000. And again, those constant numbers are there to equalize the equation to get you into the units that you can recognize. You can't be taking kilos and can't be using, in the metric system, you can't be using, for instance, a cubed dimension with a squared dimension. You have to come good for that. And that's what that does. There are people out there that are way better at mathematics than me, I guarantee you. Because of that, I love to use this little triangle. I can remember a triangle. However, some of the complex math I have an issue with. I'm a wrench twister, after all, and a wire puller. I fix things. I don't design things. I like to know how they work. So volume, again, is in centimeters cubed. The flow rate is in liters per minute. And of course, the time is in seconds, or in some cases in minutes if it's a very large cylinder. So you see the three equations that we can get out of that triangle. Volume is equal to rate times time. And you have rate, which is equal to volume divided by the time. And of course, time is volume over the rate at which it happens, which is pretty self-explanatory in that case. Okay, so here we have a regenerative circuit hookup. Now you'll notice on the top it's regenerative, and on the bottom diagram it's how we normally do it with a normal, well, I shouldn't say a normal system, but the systems that we have been using up to this point. Now in our lab, I hooked it up exactly as the diagram indicates, although when you look at the spaghetti factory of hoses on the lab table, it sure doesn't look like the nice, neat diagrams that you see. And that is, of course, what the advantage of a schematic diagram is. It shows you in an elementary form how things are connected and how things logically progress. So in the top diagram there, we have fluid coming out of the pump going to a supply manifold. Out of the supply manifold, we have it going to a flow restrictor, which is a speed device with a check valve in it. And right out after that, we have a flow meter, which tells you in liters per minute how much flow is coming out. And you will notice that when we do the experiment, that there is less fluid flowing when we extend the cylinder than when we retract it, because the pump isn't working as hard, because the fluid is getting put into that second manifold there, that second directional manifold, which is close to the directional control valve, adding fluid back into the circuit so it doesn't have to come from the pump. The bottom circuit is very much what we're familiar with, and you'll notice in the lab video the way I do that is I will just simply remove the hose from that manifold and plug it right back into the B port, or in our case in the experiment, into the A port. It's irrelevant. Notice that in the top regenerative circuit, one port is used, and in the bottom circuit, both ports are used, even though the cylinder works in both directions using that one port. It's kind of a neat feature of it. However, we are changing speed of the extension for force. And you will notice that when we put on the spring-loaded device, we generated about 3 was it 300 foot-pounds? My apologies. The scale was in imperial units. You can do the calculation for that to change it over from imperial to system international or metric by using the multiplying factor. I don't know what that is off the top of my head, but they sure have it written down somewhere. And you are going to have less force applied, but greater speed, which is why you are going to probably in an actual process use a four-way valve. Now, the four-way valve allows you to have the speed of a regenerative circuit plus the force from a regularly hooked up circuit. So you get best of both worlds scenario there. And that way you can determine, what the process can do. For instance, if I'm punching out a lot of pieces of steel, I don't want to bend steel or metal too fast. It can make it brittle by annealing the metal, heating it up internally, and forming micro cracks. So I may want to use a lot of force slower to bend that metal once the die hits the metal that it bends. But getting that die to the part, I can use the regenerative function to increase my throughput time. So we'll just give you an example here of how you can calculate the speed. So here we're going to calculate the extension time of a 2.54 centimeter diameter on the cap end cylinder, and that's the small cylinders we've been using in the previous 4 labs. And it has a 1.59 centimeter diameter rod end. The result of that is we're going to have about 2 centimeters of area on the rod end, and we're going to have approximately 5 centimeters on the cap end. So that 60% ratio that we've been talking about all the way through these labs. It's kind of easy to keep it in your head. Really, hydraulics, if you're looking at it, a lot of times you will use that force area pressure calculation along with the VQT equation will get you most of the way home in a lot of the design parameters if you're designing things. But I digress. So we're looking at this. The extension on this cylinder is 10 centimeters or approximately 6 inches. It's not a very big cylinder. And the flow rate is 1.5 liters per minute. There's not a lot of fluid in that cylinder. You're looking at something that's, 5 centimeter area by 10 centimeter stroke. So 5 times 10 is 50. So it's about, 50 milliliters, 500 milliliters is one of those two. Anyway, regardless, if I use the equation from the previous slide, the extension time in seconds is going to be equal to the rod area in square centimeters times 60, which is 60 seconds in a minute, of course, times the stroke length in centimeters, divided by the flow rate, liters per minute, times 1,000. And that gets you for, your milliliters to your liter. Okay, so the result of that is I have 1.98 square centimeters times 60 times 10.16 divided by the 1.5 liters per minute times 1,000. And I get a speed to extend that cylinder of less than a second, about 0.8 seconds. And you notice that in the lab that those cylinders extend very quickly. There's no load on them per se, and they're not very big. The pump has way more capacity than the cylinder has volume. As a result, they fill very quickly. This is why we use the flow controller to slow down the fluid, or quite frankly, to meter the fluid. So you can see the retraction. And you notice when I really crank that flow control down to almost it's choked off, that you can really see the cylinder slows down in its deployment and its retraction, but you still see the speed ratio, right? And if you put a stopwatch on it, you could time that. And in the lab, it asks you to do that, but well, let's be honest, that seems a little tedious to me. I can observe it, and that's good enough. Okay, so let's look at a practical circuit for a minute. Where am I going to use this regenerative circuit? Again, metal press is a perfect example of this. You're not going to find it on an excavator or a loader per se, but you will find it in process equipment quite a bit. In a practical application, a four-way valve is used to get 2 speeds for the cylinder. In some processes, to increase the throughput time and decrease the reset time, a cylinder can be used in regenerative mode to reach the point of work. And then we're going to reduce the speed and increase the pressure to actually do the work on this on the part, and then retract it and start it again. Bending metal, again, is a good example of that. You want to bend metal, I wouldn't exactly say slowly, but you want to make sure that you bend metal at a correct speed, that you don't overstress the metal and put micro cracks into it and degrade the quality of your finished part. For instance, if I'm making L brackets for shelving or something along those lines, they have to hold up the shelf. The weakest part of that would be the bend, the 90-degree bend in that shelf bracket. If that bracket has been annealed or has micro cracks in it from being bent too fast, the metal has to get out of the way after all, it won't hold up the shelf and it will fail. And most of the time when metal fails, it fails catastrophically. So let's take a look at the 4 pictures in the diagram there. In picture A, in the top left-hand corner, of course, everything is closed off and it's a closed center position. There's actually 2 center positions on this one. The top is the straight through. The second from the top is the closed ports. The third one is your actually regenerative function. And it's similar to one that's used in a motor. The B links back to the A and links to the pressure from the pump, and the tank is actually shut off because we're not sending the fluid back to the tank. We're sending it back to the cap end of the cylinder. In the B position, the top right, we actually have it in the regenerative, and it's rapidly expanding because it's recycling that fluid from the rod end back to the cap end. As a result of that, the speed increases. Now, once we get to the load, as you see in diagram C, we will flip that back to a normal functioning or traditional functioning cylinder where we can drain that rod end directly back to the tank, so there's no actual pressure on the rod end. It's just vented directly back to the tank. That allows the pump to develop full pressure on the cap end to do the work. And then a normal retraction speed when we flip-flop into the 4th position on the bottom right hand, or D, of diagram. So you can see that that's how it would be practically put together, right, in a real process. I can also accomplish the same thing with 2 valves. 2 simpler valves can do the same thing. In our particular lab, as I mentioned in the lab, since we don't have a 4-way valve and we don't have 2 valves or directional control valves, the only type of directional control valve we have is a closed center one. We simulate the regenerative by using the manifold, and the manifold returns the fluid to the upstream side of the directional control valve, but it is still supplying pump pressure. And you will notice that when the cylinder is fully retracted, there's still pressure on it. And the reason for that is the pump still has, through that manifold, a path to that rod end of the cylinder that's independent of the directional control valve. As a result of that, there's still pressure applied. And that would be a dangerous situation in a real circuit because you would always have that live line. And there would really be no way to isolate that correctly it would be very difficult to isolate that. I wouldn't say there would be no way to do it. Of course, you're not going to work on a machine when it's running, or you shouldn't work on a machine when it's running, but that is something to be aware of in the way we have it hooked up. So it's very important when you're using these labs that you make sure that those hoses are seated on there correctly. Even though there's a check valve inside each of those hoses, if it's on 75% of the way, it can pop off and eject fluid when it does it. But I digress. So in conclusion about regenerative circuits speed up cycle times. They can use a smaller pump. Because they're using a smaller pump, less power is used by the prime mover. And if less power is used, you're saving money. You don't get something for nothing. An increase in speed will lead to a decrease in force because of the fact that we have the rod end supplied with pressure at the same time the cap end is. And the reason it extends at all is due to the difference in the area between the rod end and the cap end. If I had a two-way cylinder, which has the same amount of area on both sides, a regenerative circuit would not work. The thing wouldn't move. It would be pushing on itself with the same amount of force on both sides. So often in practical terms, we're going to use a four-way valve or two simpler valves to accomplish the regenerative action. Wow, that's a tongue twister. And cycle time can be reduced, which is good for large throughputs in a process. So those are some of the cool things that are properties of regenerative circuits. Have a look at the notes, answer the questions in the notes, and we will talk to you next time. Next time we're going on to some pneumatics. So the next couple of lessons will be on pneumatics, which is very similar to hydraulics, except now instead of using a liquid that can't be compressed, we're going to use a gas which can. And there are different issues dealing with pneumatics that we're going to get into. All right, well, that's it for now. Enjoy the lab, and we'll see you next time.